Hey class, it's Mr. Roy here. We're going to talk about our next step in our energy journey today. We're talking about gravitational potential energy. This video is to give you a further grounding in your understanding of gravitational potential energy because you've already seen the flipping physics video about it, so that'll give you a good conceptual idea. I'm going to talk about a couple of things that we're going to do a little differently than Mr. P referenced in that video as well that I think are important or I think match up better with the particular resources that we're using. So our learning goal for today is to be able to calculate the gravitational potential energy of an object. So you probably have a pretty good idea about that already from the video with Mr. P. I'm going to take you through a few more points here. So yesterday I did that thing where I was holding a book and dropping it on the desk. Um, we noticed that something, if I'm holding it up in the air, has no kinetic energy. It's not moving at all. But as soon as I let it go, all of a sudden, it has more and more and more and more kinetic energy as something falls towards the ground. So where's that energy coming from? The idea is that energy is a stored form of energy, and that energy is stored when we do work against Earth's gravitational field. So by lifting something up, we are away from the center of the Earth. We are giving that thing gravitational potential energy. It can be there because of the mass of the Earth and Earth's gravitational field. And then when we let go, Earth's gravitational field, the force of gravity will do work on that object and will convert some of that gravitational potential energy into kinetic energy. And so that's the relationship we're talking about, that those two things are related and they can be transformed from one form, from gravitational potential energy to kinetic energy and back through forces doing work on them. Okay, so first of all, let's have a little look further about what we're talking about here. So an object suspended in the air has the potential to fall. And of course, that means it can start moving and will have speed and therefore kinetic energy. So here's the kind of situation we're talking about. At the very top of our journey, that object is going to have an initial velocity of 0 meters per second before we, or just as we drop it, it's not moving. So it has initial velocity of 0, and that means its kinetic energy up here, because the velocity of 0 is also 0. Gravitational potential energy, what is it up here? Well, we're not sure, but we're going to talk through that. We've got a height that it's going to fall. Of course, we've got our acceleration due to gravity. We've got some final velocity we don't know, and we know at the bottom it's going to have a kinetic energy of the mass times velocity squared divided by 2. And so these two things, our kinetic energy and our gravitational potential energy, are connected and in fact are going to be equal to one another in terms of the energy in our mechanical system. The gravitational potential energy here at the top, the kinetic energy here at the bottom, and when you add the two everywhere in the middle, it's going to be the same amount of energy. So that energy in that fall is transformed from gravitational potential energy into kinetic energy. So let's do a quick little derivation just so we know where this formula comes from. Yesterday, I kind of showed you the formula and I talked about the things involved, of course, are how strong the Earth's gravitational field is, the mass of the object, and the height that it's raised up. So that makes sense, but how do we know that we can just multiply those three together? Let's take a quick look at our formula. So let's start with our kinetic energy formula. The kinetic energy at the bottom is based on final velocity. But final velocity, of course, is related to initial velocity, acceleration, and height by this kinematic equation right here. So we're going to use that kinematic equation again. So we're going to replace final velocity with vi squared plus 2ad. So this whole right part of the equation will sub in for the final velocity. Next, we're going to replace the initial velocity with 0, since when we're talking about dropping an object, it's starting from rest, so we'll put that as a 0. We'll rearrange our equation without that 0. Now we're going to replace a couple of things. The acceleration we know is acceleration due to gravity, so we'll replace acceleration with g. And we'll also replace our displacement with h for height, because we're just interested in how far things go up or down. Left or right doesn't matter, because the force of gravity is down. So it has no effect and no relationship to left or right movements, right? When we're talking about work, we know that the force and the distance have to be, we're interested only in the parts that are in the same direction. So we're interested in the height from our final landing place. So when we cross out the 2 and 2 and they cancel out, we're left with mass times g times h. And this is going to be our formula for the amount of gravitational potential energy. Again, this is going to be in joules. Now, this is the one I'd like you to write on your goldenrod colored sheets. You'll notice I've made one small change. I've put a delta H because that is change in height. Your textbook doesn't write it that way. I personally think it's much more clear when we're talking about a change in height from one spot to another. So this is how I'd like you to record it on your goldenrod sheet. So let's stop the video for a moment so you can add that to your formula sheet, this new formula for gravitational potential energy. Okay, now that that's done, moving right along. Let's talk about reference levels. This is really important. This is as important as setting up directions at the beginning when you're solving kinematics equations. Okay, so this is something you have to do at the beginning of a problem. You have to draw a sketch of what's going on in the problem, and you have to indicate where your reference level is. And here's why we do that. So if there's a hole under us, just imagine that goes all the way through the earth, and you step into that hole, what's going to happen is you're going to fall, and you'll fall actually past the center of the earth, and then you get pulled back, and then you get pulled back, and you kind of oscillate back and forth, and you'll end up in the center of the earth. And of course, it's really, really hot there, so that would be a horrible way to go. But the idea is that we essentially have a certain amount of gravitational potential energy in reference to the center of the earth, the center of mass of the earth. And so really a difference of moving up, say 10 meters compared to the center of the earth, the distance from the center of the earth is very little. So instead of talking about our gravitational potential energy in total related to the distance to the center of the earth, we're only going to talk about the change in gravitational potential energy. So it's really important when we think about this and we think about our formula here, that we really think about this formula as a change in gravitational potential energy, not a total gravitational potential energy, because that would be related to the center of the earth. So I'm gonna add that in on our equation here. You can add that to your formula sheet or not, depending if you think you need to remember. Okay, there, I've added it in. So we're talking really, when we're talking about gravitational potential energy, we're talking about how much it changes over that change in height, not a total amount like kinetic energy. So that is an important idea. All right, so compared to someone at the center of the earth, we have tons of gravitational potential energy. So instead, we're going to pick a reference level, right? And we're going to calculate our difference in gravitational potential energy from that reference level. You usually want to pick your reference level as the bottom of the problem. So often the ground or the lowest point an object will go in the problem. As you saw in the flipping physics video, this reference level, I think Mr. P called it a zero level or 0 point. That's not going to move around during the problem. That's something you set from the beginning and you stick with. So usually we choose a reference level at the bottom of the problem, but that does mean that we can have negative gravitational potential energy if something moves below the reference level or starts below the reference level. If it's starting below the reference level, a negative gravitational potential energy would tell you how much energy it would need to raise it up to that reference level. So let's have a little look at what that might look like. Here's our street corner. Here's a flower pot falling out of a window, probably about to land on this poor physics student's head. So hopefully they'll jump out of the way in time. Of course, down in the sewers, we have our Ninja Turtle here. So let's take a moment and I'll set some stuff up for this. Okay, so here's our setup. We're going to call this our reference level, and this is where we're going to say our height equals 0. Now, in Mr. P's video, he talked about how we're referencing the center of mass of an object. I don't really agree with doing it that way. To me, that doesn't, although that might be more precise, for a human, we don't stand on our center of mass on the ground, we stand on our feet. And when something hits the ground, it doesn't hit the ground with its center of mass, it hits the ground with the bottom of the object. So when we do these sorts of problems, we're going to reference things from the bottom of the object. Okay, so if I want to set up a little situation here and figure this out, I can have a look at the gravitational potential energy of my different objects. So my human here, compared to the reference level, has 0 gravitational potential energy. Compared to the reference level, my flower pot is a ways up. So it's all the way up here. That's the height of my flower pot. From the reference level to the bottom of the flower pot, it has positive gravitational potential energy. So someone carried it up the stairs and through that, doing that work on the flower pot, gave it gravitational potential energy. My Ninja Turtle, on the other hand, down in the sewers, has negative gravitational potential energy. And in order to have 0 gravitational potential energy compared to my reference level, would have to climb all the way up to street level and then would have 0 compared to my reference level, 0 gravitational potential energy. So to get rid of that negative gravitational potential energy in comparison to the reference level, he's got to climb up to street level. In each of these cases, we could, of course, use our formula. So for the flower pot, we'd say the gravitational potential energy of the flower pot is the mass of the flower pot times g times the change in height from our reference level. And that's how much gravitational potential energy it has compared to our reference level. Our person, of course, our delta H compared to our reference level would be 0. And for our Ninja Turtle, our delta H would be negative because it's below our reference level. So he would end up with his, compared to the reference level, negative gravitational potential energy. Okay, wow, we got Ninja Turtles and falling flower pots in there. All right, so it's time to work on some of these problems. It's time to try this formula out. Time to put it to the test, and I'll be back in a little while to chat with you about total mechanical energy. Good luck, work hard, work smart in your groups, and let's get some practice.